I left when I found out I wasn't going to be in any of my core classes.
Yesterday, I only had the other class. But I'm trying to teach everything I need so we can do experiments for the rest of the year. We learned about titration. You can get a more accurate definition from the video or just Googling titration. That's literally what I copied it from yesterday. Titration is basically a method for determining the concentration of an unknown sample. The basic idea is you can do it in a few different ways depending on whether or not you're testing. So there's 4 categories. There's strong acid with strong base and any other combination of strong and weak. So you could have a weak acid with strong base. You could have a strong acid with weak base or a weak acid with a weak base. So choosing one of them, you might want to start with, let's just look at strong acid with strong base. You have some sample with unknown concentration. Hello? Yes. Sure can. The counselor needs you, Buck. The counselor needs you. So let's say we have X molar NaOH. We don't know what concentration this is, but we want to figure it out. What can we easily do with it? What's some properties we can easily measure? So we're trying to find molarity. What is molarity? Molarity is what? It's a measure of what? It's a measure of the number of moles to volume. And we always measure the volume, and the number is based off of 1 liter. But so what can we accurately measure? Very easily. Volume. Volume is very easy to measure. We put it in a tube that has measurement marks on it and read it. So we can accurately know the volume of this. And the only thing to figure out concentration is number of moles. So let's say we take some sulfuric acid and add it to this. And let's say our sulfuric acid we know is exactly 1 molar. We know that this sulfuric acid is exactly 1 molar. How can we count how many moles of sodium hydroxide we have in this beaker? Well, we know, first of all, what's the equation for sulfuric acid? I should be able to just look at the word sulfuric acid and instantly tell me what it is. Sulfuric acid versus hydrosulfuric acid. The word acid in both cases tells us it has an H plus ion. The word hydro tells us it's binary, so it would only have a S. The word ic without hydro tells us it's 8. And what is sulfate? So that tells us it has sulfate. Sulfate is SO4. Sulfur is in group 6, so its oxidation number is +6. Oxygen's oxidation number is -2 always. There's 4 of them, so we have -8 plus +6, so it has a charge of -2. That means we need 2 H plus ions, so the equation is H2SO4. That is sulfuric acid. So we have H2SO4, and we're reacting it with NaOH. This is the products. Products on the left. This is the reactants. What would the products be? What does this make? So this side is reactants. This is the things doing the reacting. And this side will be the products. What are the products? So we have H plus. This is double displacement with OH negative. H plus and OH negative. That's a very common reaction. That makes water. Have this one memorized. Anytime you see H plus and OH negative, you get water. And the other replacement involves putting sodium with SO4. So we have Na plus and SO4 2 negative, which would be 2 sodiums for every 1 SO4. This is actually a bad example to use. I'm going to stop it and change to something else. I didn't realize this is going to be a 1-to-1. No, it's not. No, it's not. Never mind. This is good. So what would be the coefficients? So I have 1 sodium here and 2 sodium there, so we can immediately double this up. We now have 1, 2, 3, 4 hydrogen on this side. 1, 2. We need to double that. So now we have 4 hydrogen. 4 hydrogen. We have 4, 5, 6 oxygen. 2 plus 4, 6 oxygen. 2 sodium. This is balanced. So what this tells us is for every 1 molecule of sulfuric acid, we need 2 molecules of sodium hydroxide. Which gives us 2 molecules of water and 1 molecule of sodium sulfate. So what titration does is we usually add some sort of color indicator that is very tuned to the acidity. If it's very acidic, for example, maybe it's orange. Or if it's very basic, maybe it's pink. And so if we mix 2 molecules, for every 2 molecules of this, for every 1 molecule of this, we don't have any more acid or base. This is our acid. Acids have H plus ions, and this is their base. We neutralize it. So if we know the concentration of this molecule and continually add it to this until we have no more base, until we completely neutralize this base and neutralize this acid we're adding into it, we know that the moment we add that amount, all the base is gone, and we can calculate from that how many moles it has. Does that make sense? So let's suppose we did this. And let's suppose we ended up, let's say that we started out with 100 milliliters of NaOH, and we put into it 20 milliliters of 1 molar sulfuric acid. What would the concentration of this be? So we have H2SO4 reacting with 2 NaOH, making 2 H2O and Na2SO4. So we have 100 milliliters solution of sodium hydroxide with unknown concentration. We add 20 milliliters of sulfuric acid. By the way, I'm making these numbers up. I don't know if this is possible. I'm assuming it is based on intuition. 20 millimeters of 1 molar sulfuric acid. What is the concentration of the NaOH solution? So why is this? This is actually very important to do in chemistry. In fact, if you take the college version of this class, you'll spend a lot of the time in the lab doing titration and becoming very, very frustrated. I'll go into why it's frustrating to do in a little bit. When I actually show how we figure out. So we add 20 millimeters of sulfuric acid to neutralize it, I should say, to neutralize it. So 20 millimeters of sulfuric acid neutralizes. Well, I'll talk here in a little bit how we know that it was neutralized. So we know it's a 1-to-2 ratio. We have this information. We're given the volume and molarity of sulfuric acid. From this information, what can we find out? If we know volume and if we know molarity, we can get moles. So we're given 20 milliliters of sulfuric acid. We know that 1 molar sulfuric acid means 1 mole per 1 liter. And I should say 1 mole. And we need to put in the ratio that there is 1 liter per 1,000 milliliters. So millimeters cancel out, liters cancel out, leaving us with moles. So 20 times, and we can ignore all the ones, so it's 20 divided by 1,000. So that is 0.02 moles of H2SO4. So how many moles must have been in the 100 millimeter solution?
0.02.
So again, it's 1 molecule for 2 molecules of this, or it's 1 mole for every 2 moles of this, or it's 0.02 moles for every 0.04 moles. Whenever this acid neutralizes this base, it does it whenever the ratio is twice the base for every 1 acid. 2 base molecules for every 1 acid molecule, right? So at the point it's neutralized, the point they both react fully, is whenever we have twice as many molecules of this as this. So based on this equation right here, we know that we have exactly 0.04 moles in the 100 milliliter solution. And we're trying to figure out molarity. What is molarity? It's moles per liter. So you come over here, 1,000 milliliters per 1 liter. Millimeters cancel out. And we see we have a 0.4 molar solution. And that's our answer. So, in other words, if you mix 1 molar sulfuric acid, if you mix 20 millimeters of 1 molar sulfuric acid with 100 millimeters of 0.4 molar NaOH, all the molecules of H2SO4 and NaOH will react with each other. It's only whenever you use this combination do you have every single molecule react. Now, obviously, you won't be able to precisely put it down to exactly 1 molar, or 1 molecule accuracy, but theoretically, if you had this combination and these numbers were precise, you knew it exactly down to 1 molecule, this is what would happen. If you had this ratio of that with that ratio of that, they'd all cancel each other out and you'd be left with pure water and sodium sulfate. We also talked about pH. pH is a measure of how acidic / basic something is. The symbol brackets refer to concentration. They're also used for dimensions too in mathematics. So pH is equal to the negative log of the concentration of H plus ions. More accurately, pH is equal to the negative log of H3O plus ions, but we'll get to pH later. The importance of this bringing pH is it's a scale that goes from 0 to 14. We can get negative numbers too. And water is considered neutral. And it sits at 7. Strong acids are over here. And strong bases are over here. By the way, have you ever dealt with logarithmic numbers? Have y'all ever heard of decibels? Like how you measure sound? Earthquakes. So, earthquake. There's a 7.1 earthquake versus a 6.1 earthquake. How much stronger is this earthquake than that earthquake? How much stronger would an 8.3 earthquake be compared to the 7.1 or 8.1? So y'all have never looked at log plots, like log plots and anything in math, algebra? So the difference between 7 and, or I shouldn't use 7. The difference between a base that is, or let me use acids. So the difference between a acid with a pH of 6 versus an acid with a pH of 4, 5. This acid here is 10 times stronger, 10 times more acidic. 6 versus 4. 4 is 100 times more acidic. 6 versus 1. That would be 10 to the 5 times as strong. So 10,000 times as strong.
So then, if water is neutral, why does where does the marketing with the pH come from on water bottles? Like, if you buy a $4 bottle of body armor water, there's like this whole pH scheme, but if you buy a normal one, there's nothing about pH on it.
I don't understand.
Like when you go to buy a water bottle, some of them talk about like having better pH than the other one.
So it's probably saying it has closer to 7. So if you were to go get tap water, it'll probably be slightly basic. It'll probably be, I'll actually look it up.
Because I know like body armor and Fiji, they say on the bottle they have something different.
So true water has 7, meaning it's not acidic or basic. So pH of tap water. So tap water is between 6.5 and 8.5. And depending, so EPA recommends your tap water to be between these values. In the United States, it actually can get down to 4.3 to 5.3 water. So slightly acidic. And I should illustrate, because of this logarithmic value, a 5 is not very much different from 7. That's 20 times as many H plus ions than water has. Again, water, if you have a glass of water, it's going to have a very, very small amount of H plus and OH ions in it. So it's not like water has no ions in it. It just has the perfect ratio of H plus to OH negative. They're constantly coming back, and this is a small number. I believe it has 10 to the negative 7 ions per liter. Oh wait, no. Its ratio, its concentration is 10 negative 7 molarity of H plus ions. So a very small amount of ions in it. And then we compare it to that. So this would only have 20 times that number or something. When we get to strong starts around 2 to 3. This is when you start having a really bad acid that you need to worry about. And then if you get to 1 to 0, that's where pull out your gloves and glasses before you handle it, as you could seriously hurt yourself. Like, for example, the vinegar we were using, I'll actually look it up. 5% vinegar pH. So the vinegar that we used in lab was 5%. Its value is 2.5 to 2.7. I would pour that self on my arm. I would wash it off after a few minutes, but I feel comfortable with that. It depends on the acid too. After a while, it would start dissolving your arm if you left pure vinegar or 5% vinegar on your arm. But it's by the time it starts hurting, you can wash it off without damaging yourself permanently. And pH of Coke. pH of Coke. pH of your Coke is about 2.3 pH. Sulfuric acid, 1 molar. pH is 0. 1 molar sulfuric acid is at 0. Concentrated at 98% is take 0 to 0.3 since I'm looking up for 1 molar. Anyway, I'm bringing up pH not to actually analyze what pH is. Where is it? Titration Phenolphthalein. What website did I use? CHEM Guide. Alright. Phenolphthalein is a chemical we use a lot. It's when dealing with a strong acid, strong base. Between 8.3, I believe it is. Let me just Google this. I need to get this precise number. It's a very precise number. There it is. Between 8.3 and 10 is a very bright pink. So if you put a drop of this into a base that is between 8.3 and 10 pH, is a very bright pink. So we start out with our NaOH. And we're dealing with a strong base that's between 8.3 and 10. Our solution will be very bright pink. Or if we do it right over here, so this is where we've added no acid. So we start out with a volume of 0. If our base solution is above 10, our liquid would be very clear. As we continually add more and more acid, there's a point in which it'll turn very bright pink. And look at the volume needed to go from no color to color, or no color. Or to go from right here being ever so slightly pink to no pink at all. It's like the tiniest speck of a drop. So, during titration in the lab, what the lab setup is usually we put this indicator in it. It's called an indicator. We get our, and we use a tube so we can measure the initial volume. And then we use a titration setup. It's basically a little funnel where we can look at volume, and we have this on-off switch right here. We take and we do very carefully, keeping track of how much volume we're using, and we add a drop, and then we swirl this up and see if it turns pink. We continue doing this until we get it pink, and then we're going to add the ever so tiniest drop until it barely turns light pink. Or we're trying to get to this point right here. We know that we're trying to measure this right here when it becomes 7. And we know that right whenever it turns light pink and the moment it disappears, we've added enough acid to the base to neutralize it. Because when we have 7, it's no longer, we have no more acid and no more base. Issues with this. What happens if you take a drop of water and put it into another thing? It might splash and you might end up with droplets over here. And what happens when you swirl liquid? What happens to the liquid as we swirl it? Which means if some of this phenolphthalein gets right here, you have a tiny speck, and we're trying to add tiny specks when we get close to this point, and you swirl it, you might see your solution just immediately go through the pink phase, and you screwed up. Our acid. So this was for a strong. This experiment. You can use phenolphthalein, but it's not very good. This is actually the better one to use it for when you have a strong acid with a weak base. Here, our solution stays pink for a long time. And once it becomes neutralized at 7, it takes a little volume to do. Oh, here it says, never mind. This would be completely useless. It's here. Here, we're trying to get it to be on this highly pink solution. We start out with a strong base. It'll be clear, and we're trying to make it be light pink colored. We're trying to stop right here because right here it's 7, and here it takes almost no volume to go between it. We can find a video. Let's see if this is any good. Add your phenolphthalein indicator. It's colorless in acidic solutions, but turns bright pink in so you add this up to the 0 marker on the barrette. Basically, you're going to try to get it to where it turns colors. I was saying it wrong. I was always going from putting the base in first. You can always go from the backwards. But you want the solution to be pink colored as your final result. I very remember in college when we did this. This is one of the frustrating things because we can have a spec up here and you can be right there, perfect solution, and all of a sudden you bump it or do something and it just messes up. So you're trying to make it get into that range. And it's at this point where you're like, yes, I've got it correct. And then your professor walks up to it and tilts the thing sideways and then swishes it and then it turns all clear again. And you don't know if you're below the limit or above the limit. Meaning, if you add more base to it, will you get pink back again? If you're below the line, then adding more means you still need to add more. Or did you add too much? In which case, you'll sit there, and if you added too much, you'll sit there, and if you don't record your milliliters at that point, then you're going to continually drain it down and realize, oops, I don't know what my value was, I need to completely restart. So why is titration important? Why is this something that you have to constantly do? Why can't you just read the bottle that says 1 molar sulfuric acid? And just say, well, I know what concentration it is. It's 1 molar. The bottle says so. What we learn about chemicals? What can they do? They can decompose. So the concentration will go down when it decomposes. What else is something? What would happen if I took a giant big pan and I filled it with Coke and I let it out in the sun for a few days and I came back and poured it back into my Coke bottle and drank it? Would it taste any different? What would happen? Well, carbonation. Ignore the carbonation. Evaporation of water. What does that do to concentration? Concentration can significantly increase. So you have two things that can happen. Your concentration could make it very dilute. And you do your experiment and you say, oh, my sulfuric acid is too dilute. This experiment failed. Or you can come over here and pour on one of your chemicals and then it blows up in your face. As what you thought was very dilute becomes very concentrated. And you didn't account for the concentration and it ended up boiling. As remember what happens when I tell you when you put acid into water, it creates energy. Oh, I never explained to y'all another thing too. I don't think. I think I did. Did I tell y'all why acid heats up when you put it in water? So when you add acid to water, one of two things happens. One, the acid, so let's look at H2 and SO4. The acid is going to ionize, which means it's going to split off into H plus and SO4, 2 negative. This is endothermic. It takes energy to break these bonds. So currently it has bonds right here, keeping them all bonded, however it's done. But it takes energy to actually break these bonds, so it gets colder. H plus is unstable by itself. It's just a proton. It likes to instead react with water to make H plus H2O hydrate. Basically, you have the proton is going to be loosely bonded with a whole bunch of hydrogen molecules. And usually it's just one, and we write it as H3O plus, which is hydronium ion. Anyway, to create these hydrogen bonds, this is called a hydrate, by the way, when you have a loose water molecule sticking to something. It creates energy, and this is very exothermic. That's why I was saying pH is technically defined as the log of concentration of H3O ions. But we like to assume that this is basically just H plus by itself, as we always assume we're in a water-based environment. And we can ignore the water. There's different chemicals, by the way. You might saw it. There was methyl orange. That turns brightly orange in acid solution. Have you ever heard of litmus? I'm sure you've all used it or at least seen it. Any of y'all had ever checked the pH of your pool when adding chlorine? Or ever done that?
I've seen some of it. Yeah, I've seen it. Oh, yeah.
This is litmus paper. It's paper that has litmus on it.
Oh, actually, we did this with our fish tank.
Or fish tank.
We did this with our fish tank.
Yeah. It turns a different color. So this one can do all the pH levels. It's green when it's neutral, red and yellow whenever it's acidic, and bluish colors whenever it's alkaline. Alkaline is another word for basic, because usually what are all the bases? The bases are usually NaOH or MgOH2, your alkali and alkaline earth metals. So my potassium chlorate came in. I ordered it on my own. I didn't go through school. It's a controlled substance, and I just shipped it to my house because, you know, it's weird. It's like warnings all going through it. I didn't feel like having to go through, because you have to order it from. You can't just go to Amazon and search for it. Which I got the list of chemicals for everything else we're going to be doing for the rest of the year. But it's regulated, which means you have to go through an approved seller because it's used in bomb making. And the FBI, I'm assuming, just watches what everyone purchases. And as long as you don't buy, you know, a ton of it, along with various other common bomb-making fuels, you don't really get stopped and arrested. Because you can't make explosives as long as you use it. There's laws. You can make an explosive, and as long as you use it immediately, you can't store it. And you can't make big explosives. You can't take 100 pounds of explosive material and use it. There's a certain limit. That's the reason why you can do tannerite. Tannerite is unmixed because the law states that if you make an explosive, you have to immediately use as soon as you mix it. So you can buy the chemicals needed to make tannerite explosive as long as you shoot it immediately after mixing it. And you can't make like 100 pounds of it or 20 pounds of it. But my potassium chloride came in. I don't know when all the other stuff is coming in. I'm assuming during spring break when no one's up here to accept it. Naturally. I'm assuming they'll just leave it outside. And it's very weird. It's illegal to ship a fuel and oxidizer together. But as long as they're not in the same box, I guess it's all right.
Yeah.
But one of the labs I plan on doing is I'm going to have y'all try to figure out. I'm going to make a solution of acid and have y'all actually figure out what the concentration is.
We just do anything Monday and then can over. Hold on. No, he had us watch 2 different scene things. And then we were supposed to start a term together today, and then we didn't because we weren't in there. So, hey, you might just wait until after spring break if you know. The girls did theirs because classes resumed like 6 period, I think. So they returned today and tomorrow. I guess we could go work after spring break. Yeah.